Hello and welcome. My name is Max Biegler, and I'm going to talk to you about merging process data and simulation for expulsion, prediction, and resistant spot welding of advanced high-strength steels. Let's jump right in. Let's see what is expulsion and why do we want to avoid it. So expulsion in resistant spot welding, it's also often called spatter in common tongue, is the ejection of molten metal from a resistant spot weld. It can occur due to a variety of reasons like gaps, bad parameters, dirty surfaces, tolerances, and it can cause equipment degradation and potentially reworking. I have a little video from my lab that shows some nice expulsing spot welds. So you can see our robotic machine and you can see how molten metal, how sparks are thrown out after and due to each during each resistant spot weld. And you can imagine that these fly around and can cause all sorts of havoc. For instance, here on the top right, we see some metal after the weld that's on top. And this is, of course, in an automotive car body plant, unacceptable, as it will cause trouble down the line, as it might be visible after painting. So what do we want to do here? We want to do data fusion, artificial intelligence to predict resistant spot welding expulsion. And we have used 500 welded spots as training data here. So these are welds that use an advanced high-strength steel and mild steel. And then we have merged data from different sources. The easiest data to get are the process parameters. So your current, your force, your weld time, all the parameters you basically set as an input in your machine. And furthermore, resistant spot welding is really useful for all of these AI topics because you get a lot of process signals from the power source itself. So the power source will measure dynamic resistance for each welded spot. It might measure electrode force, electrode displacement. And finally, in order to do some data fusion, so to use multi-source data, we also use simulation data to enrich our artificial intelligence. And in this case, we've used nugget growth data from the simulation, which you just cannot measure experimentally. And nugget growth and nugget growth rate especially are known to drive expulsion. And we use two sequential AI models. First, the nugget growth. So we predict the nugget growth with an AI model. Then we feed the results from this one into a model that does the spatter prediction. Some feature engineering information. So here, something from the simulation. The simulation helps us to enrich the AI data and make it more valid, basically, by adding the nugget growth to the model. So here we have a simulation of our stack up, so an RA1180 and AHSS and MS270 deep drawing steel. And you can see the nugget growing, and you can see also the speed at which the nugget grows. Furthermore, we can also weld with imperfections and include data about that into the model. So here we have a spring back, and you can see that the spring back closes and the nugget grows slightly differently because of the different contact conditions. How does that look before we put it into the AI? We have nugget growth based on the simulation data with increasing currents, so 6.8 kiloamperes leads to a nugget growth rate that looks somehow like that. And if we increase the current, the nugget will grow more quickly. And this is also known to be a cause for expulsion. And here you can also see a dashed line. This is a simple polynomial fit. And we have used that to reduce the data for artificial intelligence input, because you need to somehow make the data smaller and make it not time dependent for the artificial intelligence to read it. Let's look at some of the results. We have the first level of the AI model where we only feed static inputs into the model. So we only feed power, current, weld time, and all the things we set at the machine directly. And you see in this confusion matrix that always tells us how good the prediction of the model is, we have a result. So we actually experimentally, we see expulsion, and the prediction. So the model also predicts expulsion. This is an 89% accuracy. No expulsion on the other hand, 26% accuracy. So this model is actually pretty bad. So we need to make sure that we give the data-driven model more data to work. So now we use also the dynamic inputs. So these are the time series we measured for dynamic resistance, but also the nugget growth rate from the simulation. And you see that now the model quality is excellent. It's 98% and 96%. You will not get anything better with even with the best data science model. This is as good as it's going to be. The last step of this study, of this little experimental and simulative study, is to only use a small amount of the data we actually have. Why? Because we want to use the AI to predict better. And finally, once it has predicted it, we want to have time to act. So to change the process, to stop the process so that we can ultimately avoid expulsion. So in this case, we've only used 30 milliseconds of the weld data of I think 300 milliseconds weld. So that afterwards we would still have time to process the data and then to somehow alter the process. And here we see with the last confusion matrix that has static and dynamic data of only 30 milliseconds, that we still get a fundamentally good model response, but no longer as perfect as it was for the dynamic inputs of the whole process time. We would expect this to improve once we put more data into the model. Remember, we only use 500 welds here, but in a real production environment, you can generate training data for thousands of welds in a couple of weeks. So there you would have a pretty good database to make your model even better. In conclusion, I've shown a little use case for process data fusion in resistant spot welding. We want to predict expulsion and to ultimately be able to act against expulsion. It's a neural network that uses static and dynamic process data and is enriched also with simulation results. The process quality and the result quality is excellent when the full process data is used. If we squish it together and only use like 30 milliseconds of process data, we get a slightly worse model result. This is no surprise, but we expect it to be better, to get even better with more data. So in summary, AHSS joining processes really can benefit from data-based process control, and we're just beginning to learn all the little screws and all the little toys we can tinker with to make our processes better with all the data that we actually already have at this point in time. So thank you for the attention. If you're watching this on YouTube, please give us a subscribe. We're planning to put out more of these technical videos in the future, and I'm sure they can be very interesting to you. And with that, see you next time.